Hello, everyone, and thank you so much for joining us today. My name is Mia Burke, and I am Program Manager with Hanford Challenge. Hanford Challenge is a nonprofit based in Seattle that focuses on cleanup of the Hanford nuclear site and works closely with whistleblowers to ensure their voices are safely heard. This is the third webinar of our Nuclear Waste Scholar Series. We started this series to inspire action and involvement with Hanford cleanup by inviting movers, shakers, and thinkers to share groundbreaking research and experience working with nuclear waste. Through this series, we have been exploring deep time thinking, and today's presentation continues along that same theme. It is my pleasure to introduce our speaker, Vince Panesko. Vince is a retired nuclear scientist and Hanford manager who has been involved with the Hanford site for 59 years. As a retired volunteer, Vince served on the Hanford Advisory Board for 19 years. His work at Hanford included program and environmental protection management, exposure modeling, working with Hanford tank waste, writing and managing monitoring plans, technical reports, and technical reviews. Vince obtained a BS in chemistry from the University of Washington, attended the UW Medical School, followed by 1 year in the UW Radiological Science program. He also later studied fault tree analysis at Carnegie Mellon University and accident analysis from the Department of Energy in Richland. Just as a heads up, Vince's presentation will be about an hour long, and we will leave about a half an hour after the presentation for Q&A. If you can't stick around for the whole time, feel free to hop off. We will be recording the presentation and we'll share a link of the recording with everyone that registered. For everyone listening in, please put your questions in the chat or use the Q&A feature. We'll have time to answer questions at the end of the presentation. Thank you so much for joining us today, Vince. I'll pass it to you to talk about the mystery of Hanford's ancient lake beds.
Thank you. Thank you, Maya. Can you hear me okay?
Yes.
I'm coming in good. Okay. I'm Vince Panesko. It is a pleasure to be able to speak to you and share the mysteries of the ancient lake beds under Hanford. I began working at Hanford in 1963 and never heard about ancient lake beds until about 2009 when I heard a presentation on lake beds by Dirk Dunning from the Oregon Department of Energy. Then over the next 10 years, I learned more from Dirk and Dr. Stan Sobchik, a consultant for the Nez Perce tribe. I realized that many of the events which I had experienced at Hanford could be explained by lake beds. I merged my Hanford experiences with the papers of Dirk and Stan to create this presentation. And I just want to point out, without Dirk and Stan's documents early on and helping me learn about lake beds, I wouldn't have been able to make this presentation. Today, one of the major issues at Hanford between federal and state agencies is the role which ancient lake beds should play in modeling the migration of radioactivity through the soil into groundwater. If you wish to participate in the public comment meetings that will be scheduled here in the next year or two, and public comment periods for emerging documents relating to these lake bed modeling, and this will be involving the Nuclear Regulatory Commission and Department of Ecology, will have these public comment opportunities. If you're going to participate in those, you need to unlock the mysteries of the ancient lake beds at Hanford. So how are you going to do that? Well, let's say you get this idea that if you went to work at Hanford, you would imagine how you'd begin to investigate these mysteries. So let's see this, see if we can get started here and click on. Just a minute, we'll take, this is supposed to drop.
That looks good to me, Vince.
You can see it?
Yep.
Okay, I was supposed to click another time, but it didn't happen. So, okay, so what happens is that you've got this idea you want to go to work at Hanford, and you're thinking, well, how would I approach this? And one of the things you might do is, first of all, look at the ancient past and solve the mystery of how ancient lake beds were created. Then you might start with saying the mysteries created when ancient lake beds disrupted Hanford operations and how the lake beds helped Hanford operations in the past. Then you would say, well, maybe I'll look at the future today and see what the mysteries are today. What's the situation? And then, then the last, you would look at, well, what are the mysteries of why ancient lake beds are making Hanford cleanup more difficult into the future? And especially discovering the 5 future dangers created by ancient lake beds. Okay, Maya, I need to be able to, well, let's see. I see the screens. There's an arrow here, but we'll find it and get started. Okay, so you get a job at Hanford. It's your first day on the employment office. The HR person hears your search and whispers into your ear, the secrets of the ancient lake beds are hidden in the 200 areas, and assigns you to work there. And you say, what? What are the 200 areas? So they hand you a map, and you see the 200 areas are located in the middle of the Hanford project. And you see the Columbia River going through the project with Richland, Kennewick, and Panesko down in the southern part. And they tell you the history up through 1990 when we were in production mode. The uranium would be brought into the 300 areas, manufactured in fuel elements, sent out to the reactors. In a neutron environment, the uranium would be converted, some of it would be converted to plutonium. That fuel element then would be sent to the 200 areas where it was dissolved and the uranium and plutonium were recovered, purified, and shipped off site, leaving millions of gallons of nuclear waste in the 200 areas. The second day on the job, they send you out to the 200 areas, both areas actually, but 200 East is here, and there's the highway coming in, there's the main entrance, and go by the powerhouse to the main intersection. And they show you a big canyon building. Here's B plant. It's one of the first canyon buildings, operated in the 40s and 50s. And then Purex, the second big canyon building. And these canyon buildings where the fuel elements were brought in and dissolved, and the uranium and plutonium were recovered. The rest of this is just a jumble of buildings. It's a maze. You drive through this and you're confused by everything you see. There's no particular organization. You hear about tank farms and burial grounds and things, and then next the same day they drive you 2 or 3 miles over to the 200 West area, and it's the same thing, a collection of canyon buildings and miscellaneous stuff, and you're overwhelmed. There's just so much information. Each area is about 4 square miles, and so then they tell you that there's 177 tanks that currently hold 56 million gallons of radioactive waste, but you can't see any. And they're all buried underground, covered with 8 to 10 feet of dirt to provide protection for the workers. And then, well, in fact, you see a tank here, and you see it's 45, 50 feet tall, and you see guys working up here, 75 feet across. And then they tell you that somewhere between 125, around 125 million gallons of high-level waste were discharged into the ground between 1944 and 1966, and most of it never reached groundwater over the past 60 to 70 years. The light bulb goes on into your head. This could be your first clue. What happened to all this radioactive waste? High level, where is it? If it didn't go directly into groundwater years ago, where is it now? Because everybody thinks in terms of the desert out here, just a pile of sand, and if you're going to put anything in the ground, it's going to go straight down into the groundwater. So now we're reaching the question is what's going on. Well, after I presume many of you watched the presentation by Tim Connor in the previous webinar of the Nuclear Scholar Series, you understood that the melting of glaciers created a series of floods which helped create the existing geology under the Hanford site. To learn more, you discovered the website of the Ice Age Flood Institute. I'm going to put that on the screen. And this is one of the most informative websites. And I really encourage all the viewers to go to this website. If you have beautiful videos And so you can write this down now, or I'll bring it up at the end of the presentation, www.iafi.org. And one of the challenges, of course, is they have two videos there of flood simulations. Is one of them. It's a gentleman by the name of Chris Goodell's got fascinating flood simulation on there as video. One of the challenges on that website, though, is to try to find the videos. There's a couple of links, and I'll repeat these later on. You have to go to they're hidden. They're not clearly landmarked, but it's amazing, and I can't say enough about it. I can't stop talking about it. It's fascinating stuff that you can see there in terms of the videos they have. There's also books that talk about the same thing, and Professor David L. at University of Montana and Dr. Bruce Bornstad Patel here at the Pacific Northwest Lab also have really good books on this subject. We'll talk about them a little bit later. So do you realize now that after watching all these videos and Tim Connor's presentation previously, that this is what you learned. You learned that there's an ice sheet, and they have lobes, one in Montana, the Columbia lobe, the Okanagan lobe. The one in Montana started melting, and the chunks of glaciers have blocked a gap in the mountain range here and created a large lake over Missoula for 3,000 square miles. And when the water got high enough, the lake lifted the ice dam up, and chunks of ice and glacier flowed over Spokane, one of the largest floods in the history of the world, down through the scablands, and cleaned out, took all this fertile soil here and pushed it down into the Hanford area and over the Palouse area. And I should mention at this time that this water that came down extended over a vast area all the way up to Yakima and over Walla Walla. We'll talk about in another minute. But what happened is at Wallula Gap, there was a blockage, and the ice chunks and all formed the dam and formed a giant lake. The lake was like 2,000 square miles. And here's Wallula Gap. And it used to be narrow. It's eroded. And it's deeper because there's a dam down 10, 15 miles, McNary Dam, blocked it up. And so there's 200 feet of water right here. And so this gap would block the ice chunks would form here and create a lake. And you can actually see some lake bed images here on the line. If you're in the Tri-Cities, you can go take a couple hours and go over to Panesko, and well, there's a highway that goes right along around here, and you can drive through that all the way down through the Columbia River to Hermiston and back up the Tri-Cities. You'll get a view of that. And if you're more energetic, you can actually take hikes. Dr. Jordanstad's book has some hikes that you can climb up to the top of these corners here and stand and look down several hundred feet. And not to my anyhow, my liking. I don't like the edges, cliffs like stuff. Anyhow, there's a giant lakes formed behind this, and the depiction of a lake. Bjornstad made this, and Hanford documents used this picture to show that the lake formed behind this would go almost over Badger Mountain and Candy Mountain and would cover Richland, elevation 350, with about 800, 900 feet of water. And a couple things about this lake: it extended all the way to Yakima. It covered Walla Walla with 50 feet of water, and up north to Othello and Ephrata. It was huge. But here in the Tri-Cities and Hanford at 800 feet, imagine the pressure of 800 feet of water on the sediment that was washed down in the floods. And it created these lake beds that are very, very hard. And there's a discussion over how many times this happened. So that's still discussion is ongoing. If you're in Richland, one of the hills, the Badger Mountain overlooking Richland, has hikes, and you can take a hike. If you got a couple hours, you can hike up there, and near the top, you're going to find this monument to Lake Lewis, a maximum elevation of 1,250 feet. Imagine standing here and seeing this lake 2,000 square miles, all covering Richland and Hanford north beyond that. So also in Richland, in the summertime, you have an opportunity to take a boat trip up to the Columbia River, 40 miles up the river. And the captain of the tour boat will tell you that here's Hanford on the left-hand side, and on the right-hand side is what we call White Bluffs. And if you notice these striations in there, the captain of the boat tells you, well, these are ancient lake beds, and that these lake beds, there's 30 or 40 of them here, cover Hanford in the Columbia River, sliced through this hillside here, showing these things. So let's see, at this point, this summarizes what you've learned so far about how lake beds were created. And now the next question is, how did the past Hanford activities get disrupted? So that's the next mystery that we have to solve. And so one of the first documents that revealed something about geology under Hanford was written in 1947. And what this document said is that it was 18 million gallons were put into 3 different lake beds, liquid disposal sites. And one of the things they noticed is the plutonium contamination didn't go down below 34 feet. But look at this, it went out 197 feet laterally. Okay, what's going on? Kind of interesting. They didn't expect this. Fission product contaminations, there's different sites here, but one of them 28 feet deep went laterally 280 feet. Well, they looked at this and said, this is good news. I mean, we put 18 million gallons of radioactive waste into the ground and it never reached groundwater. And so they got the idea that they could keep doing this, and they did. And it went on for decades with the notion that you could put large volumes of radioactive waste into the ground and never reached groundwater. And what we're going to do is go timeline chronologically and see what how this evolved, other past events. So you can see that they didn't know these were lake beds at the time, but they knew that something was going on about lateral flow. The east area is outlined in green here. And from this viewpoint, again, there's Purex and there's B plant. This happens to be the waste treatment facility under construction right now. What I want to point out to you is that here's an area outside. And back in 1952, they ran out of space in the tank farms behind B farm. And they're behind this burial ground sign. You can't quite see there's nothing to see anyhow. The tanks are all underground. And they decided, okay, they didn't have to dump to keep operation of the B plant and Purex at the time. They had to get rid of 25 to 30 million gallons of high-level waste out of the tanks, which would be, and then they went and put a pipeline in over to this area here called the BC cribs. Well, what is a crib? Well, we'll see that in a second here. Bring it up. This is an outline of the BC cribs. So there's 6 of these cribs, and those are little boxes. And a crib is built of, they call it a crib because it's kind of like a baby crib. It's built with wood. You got this wooden slats. Sometimes they're interlaced with each other, 10 feet square, 15 square, 10 feet deep, sometimes full of rocks. They put a pipeline in there and they dispose your liquid into that. And there's all kinds of different liquid disposal sites. This happened to break through to groundwater, and then they just stopped using this area and they went over and built trenches. So here again, the liquid disposal site has a trench, could be a square box. There's a wide variety. We can't get into details all of them, but anyhow, they distributed that material and it never reached groundwater. And we're going to come back to this and BC Crib area. So just kind of remember BC Crib because we'll revisit it later. But here was an example, again, of how lake beds helped Hanford operations because they, in the past, because they didn't reach groundwater. Okay, that was about the 50s. Jump to 1973. The biggest tank leak in the history of Hanford happened to T106 tank here in the 200 West area. T plant and B plant over here were the two first original reprocessing plants in the Big Canyon building. So anyhow, that tank leaked 115,000 gallons, and by golly, it didn't go to groundwater. It was trapped, and it's still trapped today. And okay, so there's another example of lake beds helping you. This is one of my favorite stories. In 1979, they were just finishing the AN tank farm, brand new tank farm, and they needed dirt to fill in around the tanks. And so they cut a hole in the fence here, and they went over outside the 200 East area and started digging up this dirt sitting out here, and they called it a burrow pit. Maybe it's borrow pit, I might have misspelled. Burrow pit for AN tank farm. And they took the dirt over and backfilled it in almost to the top, and they accidentally took a radiation reading. I'm not sure why, but they took one and found, by golly, it's radioactive. Well, tanks haven't even been filled with radioactive material yet. And the tank farm has already got radioactive material. I happened to be manager of environmental protection at the time. So they called me up and asked me to come over and try to figure out what's going on. So I put on my protective clothing and grabbed a radiation monitor and ran down into the burrow pit here. And I found this layer of hard pan down at the bottom of the trench. And it's a layer is only an inch or two thick. And on top of this layer is about 4 inches of wet soil. And it had this organic smell to it. And it was radioactive, just the 4 inches. And it was only on top of the hard pan. And it's 1979. I never heard of ancient lake beds. Nobody, even there's not anybody's vocabulary. So what happened? Well, we figured out that A and AX tank farm were here, and they received boiling waste from Purex. And later, the temperature still was a lot of moisture coming off these tanks, radioactive air, and then we put it through the steam, put the steam through condensers, and the condensate then was sent over to an underground liquid storage site we called the crib again. But this was shaped not like a box. This actually had a piping system, and we expected all that contamination to go eastward. Well, what happened was there's a dang lake bed sitting here about 20 feet deep, and then the flow went north and into an area that was determined, we knew was a non-contaminated zone. So we had a radiation zone right over the crib, and that was, you knew not to dig there, but you figured anything outside of that crib was fine. It's a clean surface and all that, what the heck. Well, nevertheless, this ancient lake bed, it moved contamination from the A24 crib out around that area, and it's still there today. You should be able to dig anywhere in that area and find this lake bed at about 15 feet or so, with some contamination decayed since that time. So here's an example that I want you to remember for the rest of your lives in terms of every liquid discharge site at Hanford. There's a couple hundred of them, plus all of the leaks we had, major leaks sometimes, and even all of the water discharges we put in. You got to remember, I said at the beginning that there's 125 million gallons of high level waste, but remember, there's over 450 billion gallons of contaminated waste that were put in various sites. And did that all go, with all the lake beds we have, which you're going to see more of here, did that all go straight down to groundwater? No, it went sideways. And so here's the first, this was for me, my first example of seeing sideways movement, and that stayed with me for the rest of my life. And that's probably why I'm giving this talk. I had that experience. You go over 200 West area, and there's a canyon building, U plant. They had some facilities next here where they're purifying uranium before they shipped it off site, and uranium waste from that went to U1 and U2 cribs. And after a while, the uranium reached the groundwater. So they took these cribs out of service, and they built a new crib, the U16, and they started putting liquid waste in that. Well, what happened? They found out that they were taking monitoring levels here in the monitoring wells, the levels of uranium in groundwater, and the uranium concentrations went up when they started using U16 crib. Well, what's going on, folks? This isn't supposed to happen. The monitoring well at U16 is supposed to be monitoring this. You're not supposed to be getting contamination from one site into monitoring wells of another site. This should scare you. And I was manager of environmental protection for 5 years. I had to report on the contamination levels in our monitoring wells once a month to the upper management to determine if we needed to take a crib out of service or not, liquid discharge site out of service. And to find out that our monitoring wells might be monitoring something that's not even discharged. We have several other discharge sites around here, and holy cow, you just hope that the data we got over the past 80 years reflect that site, not some other site. But this is one of the dangers of ancient lake beds. They can trick you. And this is an example of where they did. It happened to be fortunate in this particular situation that these two monitoring wells for the 1 and 2 cribs were out of service. So we knew something was fishy when we started seeing uranium levels go up in those monitoring wells from the U16 crib. 1998 was a major turning point in Hanford history regarding ancient lake beds. General Accounting Office issued a report that strongly criticized Department of Energy. Now, they were correct in assuming that the waste would move slowly, if not at all. That's what we did through we call it the vadose zone, which is the soil of 250 to 300. So you'll see vadose zone all the time, but that means just the dirt underneath the surface of Hanford. And therefore, DOE never issued a comprehensive plan to assess the vadose zone conditions and funded few studies. And other people they talk about here claim that DOE couldn't credibly estimate the site's long-term risk to the public or select the most efficient cleanup strategies unless it understands the conditions of the vadose zone. And they pointed out DOE had no strategy in place for investigating the vadose zone and had low funding priority. Well, things changed. That woke things up. January 21, we're going to move a little more quickly here. Ancient lake beds were under seed farm, but try to see ancient lake beds aren't mentioned here. Beds are a few centimeters thick there's a clue. That's an ancient up to 10 centimeters. And they talk about slack water. Okay. But they didn't say an ancient lake bed. In 2002 under BY and BY, we call them the B complex. They talk about there's ancient lake beds caused a horizontal flow of migrating contaminants. Okay, that sounds to me like an ancient lake bed. Then geologists use terminology that the layman couldn't understand, and different phrases and things like that, but they never used ancient lake beds. But you start to see a pattern here. 2007, much more information, lateral flow under BC cribs. And they talked about the fact that they determined the contamination can move laterally several hundred feet away from any discharge point. And here's a good word for you if you figure that out. And you can see the language used by geologists that the layman won't understand. I'm going to take the time to find all these. But here's the interesting one. 2008, under the Essex tank farm in West area, they point out a cemented caliche layer under the entire Essex tank farm. And read this next sentence. Any tank leak from Essex would be carried laterally along the top of the caliche layer to outside the footprint of the Essex tank farm. Now, wait a minute, folks. All my life, I figured any of the leaks at the Essex tank farm and all of the piping lakes too. You got tank lakes and you got piping, and then you got accidental overflows. That's not okay. I figured that's all sitting underneath SX farm. I always had that conception and idea of how that contamination is. This sentence says no, it's not it's sitting there up to a depth of about 150 feet. It's not sitting any further than deeper than 150 feet. It flowed outside the tank farm, and they never did define how far this caliche layer actually carried contamination. SX tank farm might be, the contamination from SX tank farm might be 100 feet away from the radiation zone, the boundary of the tank farm, 200 feet, 500 feet, 1,000 feet, half mile. Who knows? They haven't defined that plume. And so here again, it shows you how lake beds caused problems in Hanford past. This picture shows the entrance again to 200 East area. And the IDF area here is the integrated disposal facility. This is a site where the glass from the waste treatment plant for low-level waste that's classified is going to be stored. 2 points I want to point out here. This Sisson and Liu site, they did an experiment here on ancient lake beds, and they put 5,000 to 8,000 gallons of water in there, and it never did penetrate the first lake bed. We're going to show you a picture taken from a pit that was dug right down here in the southwest corner of this site. This is one of the most fascinating pictures in my whole presentation. What this shows you is a couple of meters of surface area, 1.2 meters of sediment layering, and they didn't call it lake beds, and then sands. Okay, but what you see here is sand. This brown, the gray stuff is sand. What's this right here? Looks like an ancient lake bed to me. A little bit of sand, another lake bed, compressed, really tight sediment. Here again is sand, and here's lake bed. It's another sand. They dug a little bit out, and there's another lake bed, sand, lake bed, sand, and another lake bed up here. Okay, how many feet do you have here, folks? The shovel is 5, 6, 7, 8 feet. How many lake beds do you have? 1, 2, 3, 4, 5, 6. Try to figure out, try to model this. You're a scientist, and you're going to model how liquids radioactivity is going to penetrate this kind of geology underneath the 200 areas. You put liquid in, okay, maybe it gets through here, slides on, gets this lake bed. This looks pretty tight. So it's angled, so it might slide off to the right here, and then maybe it flows back to this one, and then maybe it's back and forth. Hey, how do you model something like this? It's confusing, and it's really a challenge to deal with this. Let's see, I got to go. Okay, I see where we're going. We're going to C farm right now, which is next to A farm over here. And one of the things we noticed at C farm, and this is where Dr. Stan Sobchik came into the picture with his documents. And what you see here is a borehole, and here's the depth down to 260 feet. And what this is a moisture content. Now notice the moisture content is roughly 2 to 4% all the way through. Wait a minute, what are these dots here? Why is the moisture there, here, talking 8, 10, 12? Well, what happens is with ancient lake beds, the moisture sits on top of those beds, and maybe it seeps through slowly. And see, there's some beds permanently trap contamination. Other beds are not, have a little bit of porous. They're more porous, and so they leak through, they seep through. But nevertheless, the lake beds tend to trap. And Stan learned that, okay, on these lake beds, you can see high moisture content. And we learned to do, and so what Stan did is he took a whole bunch of these wells, and he saw these high points where moisture was accumulating, and he was able to define lake beds across the entire sea farm area. And he came up with this fascinating diagram here. It's a moisture log. Notice the moisture down here, green is what you expect for most of these wells. And they are just water most of the way. But notice up here, blue means you've got a higher moisture. And what Stan found is these lake beds were crossing with wherever you took the sample, they had a higher moisture. and that moisture happened to contain cobalt-60. And so Stan was able to come up with a diagram like this under sea farm, showing that the migration of cobalt-60 was in a laterally. It wasn't going straight down like the Hanford scientists were proclaiming. They're modeling straight down. And so Stan took this sideway movement. And this is the most important. I keep saying the most, each slide, certain slides are most important. This is probably the most important document, slide rather, in the whole presentation, because this is Stan's conceptual diagram of how the lake beds underneath sea farm could move material laterally a long distance away from the farms into groundwater, like we discussed with the SX tank farm in West area. What we had been modeling up before, the Hanford modelers were just modeling vertical flow, because that's the easiest to do, and without lake beds present. So the lake beds just messed up your model. And as we told you before, when you showed the picture of all those lake beds, 6 or 7 lake beds within 10 feet, how do you model that? Well, anyhow, the modeling of this vertical flow, what it does is there's 2 or 3 elements we need to talk about. One is that it gets you to the groundwater quicker. And second, and we're compared to lateral flow, which takes a longer period of time. And this is a very important point, and I'll make that later on. You'll make that point. You will discover. So you discovered that also the second point is that vertical flow tends to be the inventory, and that tends to be smaller. It's a narrower pathway. It just zooms down into the groundwater. This pathway, where it's lateral, the inventory of radionuclides in the soil is much greater. And so if you model a leak like this from a tank or from a liquid disposal site, your time to reach groundwater is going to be faster than reality, and it's going to have a smaller inventory than really exists. And these are 2 points that are being discussed now with the Nuclear Regulatory Commission and Department of Ecology, saying, folks at Hanford, you guys aren't modeling the right situation, which Stan pointed out, is a lateral flow. Well, there's a third element to this that I wanted to take you to point out. When you saw that when we were talking about U farm, presume you had a monitoring well, right, sitting right next to this tank, and it's leaking. It could be a liquid discharge site too. And you had another monitoring well over here on a neighboring site. Well, what's happening? This monitoring well under this diagram is not showing anything, nothing, no contamination of the groundwater. Meanwhile, over here on a neighboring site, you've got contamination in your monitoring well. It's not coming from the site that you're monitoring. It's coming from this particular leak over here, sideways. So this diagram is extremely important in showing you how the ancient lake beds can mess up your mental image of what's underground at Hanford. Okay, let's see what the next slide. We're going to, again, I have to jump back in here. We're going to bee farm and just take a look at that a minute, because they had the same situation with a leak. The millions of gallons went into the ground from the bee farm. We call this a bee complex, just easier. And there's a plume trapped underground. It's a 5-acre plume, hasn't reached groundwater. And so this is, they've got it defined. And so another example of how lake beds have helped and trapped contamination and kept it from going to, so in other words, evidence of lake beds. And what they did, starting back in about 2012, they put a well into they put 3 wells into that water that's trapped. They call it perched. So this trapped water, they pumped it out, put it in a container, took it over to the 200 West Pump and Treat facility, and now there's a line on that. You're going to show that. We'll show that more. We'll talk about that more later. So let's see. We're going to Z plant. I have to go back and forth. Sorry, guys. West area over here. We talked about T-leak already, and the cribs around here in 1947, where we first got the idea of lateral flow. And then the U farm, where we had lateral flow messing with the cribs. Well, here in the middle is the plutonium finishing plant, and it had 28 cribs and over 1 billion gallons of plutonium waste within the ground. This only shows 3 cribs. This shows you the fish bone kind of on one type of a liquid discharge site. We're going to focus on the Z9, which is more of a box shape crib located next to Z. And they came up with a Z9. This is the model. And most of the plutonium was trapped right at the surface of the crib within 2 or 3 feet. But they noticed that there's a silt layer down at 65 feet that trapped contamination, and a silt layer with the caliche calcium carbonate that contamination didn't go through at 120 feet. So that's the model. That was the 65 and 120 was picked up. What this diagram shows you is plutonium in the circles and americium in the triangles were sort of posed or situated along 65 feet, and then down to 120 feet was more situated with nothing in between and nothing below. All these are zeros, and they didn't take any samples above. And so Dirk Dunning gave a paper, and he said, wait a minute, folks, you've got these 2 little numbers here. How are you interpreting? There's a problem here in terms of what you mentally think this means by getting some samples at this monitoring well right here. And he said, what's happening is people, we call it analysts, calculates the mass, potentially missing the main plume. So you're coming up with this imaginary plume. And he said, with ancient lake beds, that plume that you had before might not be the right plume at all. You have a leak, whether it's from a tank or from a purposely put on liquid put into the ground, that they hit an ancient lake bed. Where's that? It might travel sideways and then back into your monitoring well, back down to another layer and back through. In other words, the second point may not have anything to do with this with plume. And that's interesting because there's gaps in the previous diagram that we showed you. So Dirk, he raised the issue that the fact that we're doing vertical monitoring wells and gives you a bias, a mental bias, that we all have this mental bias that this liquids flow straight down. With ancient lake beds, that's not the case. You get lateral flow, and they keep saying it over and over again. This is the last example of lateral flow, and it concludes, you concluded now after looking at all these examples that, hey, the lake beds really caused a problem, but where are we today? And today, there's lots of activity related to lake beds and lateral flow. And the first one, first major activity, is dealing with how much material has seeped through the lake beds into the groundwater. And so you have a groundwater report that's very important. Also, they're going to expand that perch contamination. We have that one site only at the B complex where they had that 5 acres of perch material. They're going to add 12 new wells and look at more perch material. But you remember now, there's hundreds of sites where's the perch contamination, and we're only looking at one at the B complex. The lateral migration model developed by the Nez Perce tribe with Dr. Stan Sobchik has been included as an alternate concept model for the vertical flow as the worst case situation. They still are going to use the vertical flow model, and that's still being discussed, and there will be documents coming out for your public review. And if it's a Nuclear Regulatory Commission, they may have final conclusions on this subject, and there'll be public meetings that you could go to. But once you go to, after this presentation, you'll be able to understand what the issue is regarding these lateral flow on lake beds. And today, there's new electrical resistivity tomography. It's a fancy word for using electrical conductivity to define boundaries of perched contamination. I'll show you a picture of that in a minute. There's also new 3D imaging of radioactive plumes in fato zones. Again, I'll show you a picture. Other new technology is in situ remediation of subsurface soils, injecting chemicals to lock perch radionuclides in place. And in the last idea, there's lots of activity to develop new surface barriers over tank farms and protect them. So there's a lot of stuff going on. That's really good stuff. And so let's look at the first groundwater report. You're going to open this up and you're going to see that they'll show you the first big picture, a few strontiums and chromium leaking into the Columbia River up here. We see a tritium plume, iodine 29 plume that's crossing from the 200 west and east area here. This is all kind of messed up. There's a lot of, well, it's hard to read. We need another slide to get a little closer to that. Here's the 200 east area, 200 west area. And again, these plumes are overlapping, a little bit difficult. You can figure out some of the sign of the nitrate here, carbon tetrachloride there, and some other things, but it's hard to read. Fortunately, the groundwater report takes portions of the 200 east and 200 west and shows individual sites. So here's an individual plume of carbon tetrachloride. And what we did around the 200 west area. So we're looking at the north portion of the 200 west area, and you see this giant with higher concentrations in the middle. And what they did, you notice a bunch of red triangles pointing down here and pointing down there. They put in what's called injection wells, and they injected water. And what did they do? Well, over here in the middle of the project, they put little red arrows with the, they called extraction wells. So we injected water here on the edge, and we extracted water here from the groundwater. Now this is contamination. It's not a plume. This is contamination in the groundwater. So we're cleaning up groundwater, and then they extracted the contaminated water out of the ground and into what we call a pump and treat facility located in the middle. Here's the pump and treat facility. And they would take the radioactive contamination out of the water and then inject the water back into the ground. This gives you a better picture of the general layout. This is again shows the entire over the 200 west area. Again, with the injection wells on the outside of the extraction wells on the inside, going to the pump and treat facility in the middle. Also show this line coming over to the one extraction area in the east area. Pump and treat does not apply to the 200 east area. They haven't done that yet in that area. So those plumes, not working on those yet, other than in the B complex where I showed you that 5-acre plume, where they were taking groundwater out of that. And there's a pipeline now going over to the 200 west pump and treat facility. Now, again, I just want to show you this again. This is the same area, 200 west area, and the individual plumes. So that's all I'm going to just show you. There's chrome here, chromium, and a tea tank farm. So it came from tea plant, canyon, one of our first canyon buildings that's still in the soil. This shows iodine 29, a couple of plumes there. There's some out of the picture here as well. It's not, and here's nitrate, which is over both areas. And here's technetium. So you can go to this groundwater report and you can actually see these individual plumes or different parts of the and it makes it much easier than these other maps like this. When you see the overlying plumes, it doesn't give you an accurate picture of how to link the plumes with a particular facility. It does give you a good view of the pipeline system where the reds, the injection, the blues, the extraction, and the pipeline over to the one location in east area. Okay. This just shows the over at the B complex. And now this isn't the plume. This is groundwater. This is groundwater above drinking water limits, and this is uranium plume. Plume in the groundwater underneath the perched plume. And the perched plume is leaking in providing a source of uranium into this. And this is the one area where there's 3 wells and they're pumping both material from groundwater. They're pumping uranium. It shows you how much uranium they've moved, started from 2012 to 2020. So this shows you that there is technetiums being removed as well. And you can see in terms of how much perched uranium they got out of that trapped on the ground on the lake bed. It's what 200 for the what 300 kilograms of uranium have been recovered from there. Not as much technetium from the perched portion, but from the groundwater. And so that's what's happening today. This is whatever tomography, showing how you can use electrical conductivity to measure a plume. And this is the one case that it's an emerging technology, brand new. What you see here are the trenches of the BC crib we talked about earlier. And what they're doing, we're going to take slices through this in 3-dimensional, and they're going to move through the site here, the trench area. And what do you see? You see this red and yellow, and that is the plume. It showed nitrate. The nitrate is an indicator. Well, is in the plume, and electroconductivity works pretty good to detect the nitrate, which is the area where the contamination is. And it's interesting that they put contamination, as they say, 25 to 30 million gallons into 17 cribs spread out over the area, and it coalesced into one plume. And so it's a fascinating, as they went through the plume, you can see how the various concentrations. So they can define the plume using electrical conductivity. This is the first example of it being used on a large area like this. And it's a hopeful thing for the future in terms of being able to define future plumes using electrical conductivity. So that's an emerging technology. Other emerging technology is 3D view. If you're good with computer modeling and things, this is happens to be the uranium plume that we looked at before, and this happened to be B plant plume next to it over in East area. And but I'm just going to show you the fact that we've got this technology and it's emerging, and they're getting better at putting 3-dimensional views. Here's a multi-plumes in one spot. This is interesting with the technetium-89 because it shows more penetration going down instead of lateral movement, although there's lateral movement here at this point, lateral movement there. That's fascinating technology. Okay, what does this slide, persistent lack of lake bed knowledge, mean? Well, this is a present situation. This is the end of and you discovered a document issued by Battelle scientists September 2021. That's only 9 months ago. This is the most recent recent analysis, recent perception, recent summary of what's the situation like with lake beds. It's the most fascinating document I've got because it's new. It's just last year. And what does it say? 100 of poorly defined contaminated liquid discharge sites. Yeah, we only know plume of one, the BC cribs with electrical conductivity we just looked at. Persistent and deep beta zone resource sources, meaning you've got technetium, iodine 29, uranium, nitrate, other stuff, commingled, all posing long-term risk of continued flux. Flux means flow into the groundwater, with significant gaps of the total amount of contamination in the beta zone. We don't know how much is there. We don't know what the flux is into groundwater. And that's down here, this language down here, uncertainty associated with subsurface heterogeneity. Remember that slide with the 6, 7 ancient lake beds that we saw within 10 feet? That's what they're talking about, uncertainty, because that applies to that site. We don't know on these other couple hundred liquid discharge sites what it's going to look like under that. And so this summarizes the present knowledge, but it also gives us a baseline to look into the future, because this is what, if you're going to go and say, what's the future of Hanford? You're going to start and say, well, here's what we're starting with in September 2021. And what are we going to do in the future about all this uncertainty? Well, they talked about some other factors that come into play. The difficulty of working underground 200 to 350 feet deep to figure out where these plumes are, as well as prohibitive cost as well, the installation and pumping out of contamination. So the future, what's the future that you could figure out? Well, you come across this diagram and you find out that DOE has said, we're going to call the 200 areas industrial exclusive. Well, what does industrial exclusive mean? There's other uses we're going to skip. Does that mean future nuclear industry or non-nuclear? Now, if nuclear, it means, well, fuel preparation plants, small-scale nuclear power reactors. Are we going to have reprocessing plants for fuel in the future sometime? Continue pump and treat cleanup, or non-nuclear? And you figure out why these are necessary. And you see that you determine, gee, soil and groundwater may be contaminated for thousands of years. The area is not expected to be safe for unrestricted use for the public. The industrial use will limit access of the general public. And in addition, these industrial use means that you can leave more contamination in the ground and not have to clean it up for the general public. They're not going to be there. They're not going to be able to get to the groundwater or the soil. Therefore, you'd reduce cleanup costs. So we start looking at the dangers then. To summarize the future, what are the 5 dangers of the future cleanup at Hanford? And the first one, of course, is the radioactivity moving out of the radiation zone and being in clean areas. And all that says basically is that you need to, if you're going to do any digging at Hanford in the 200 areas or near the 200 areas, any digging, any excavation at all, you need to have radiation detection surveys, because you don't know where the underground contamination is from all those sites, how far it's spread. Danger 2 is the fact that monitoring wells might be measuring contamination from a neighboring water well. So when you put a monitoring well in or try to interpret it, you need to do some kind of testing. Savannah River used to die on testing their monitoring wells to be sure that the monitoring well was measuring the contamination in the discharge site. Danger 3 is failure to protect the perched radioactivity or the trapped radioactivity. And, we've already said there's a lot of material been put in the ground. How do you keep disturbing those zones for the next 10,000 years? What's the strategy for long-term protection? Who will prepare that strategy and when? 1998 GAO report, as you said, here's the title. Well said, DOE had no strategy in place for investigating the zone. Is that still true today? Well, 23 years later, here comes the Battelle scientists on this report that I just talked about, adaptive site management strategies. What did they say? Uncertainty with respect to plume distribution, uncertainty of total mass in the aquifer, uncertainty in currently known continuing sources. There appears to be no plan available to the public which addresses all these uncertainties. Well, have we made progress in 20 years? Well, we'll get back to that in our closing. Danger 4 is failure to control the discharge of water into soil. This is probably one of the more important ones. You discover several elements here that we know that there's high volumes of perched contamination, and but the precise location is only known in a few cases. But there's hundreds of plumes of more contamination that's trapped that have not been defined. We only know a few. Many of those activities, many activities in the 200 areas discharge water to the ground, more than you think. These discharge, where we put water into the ground is known, but there's not one map that you can find that correlates all our discharges where we put water into the ground, which we'll talk about now, with the past discharge sites. And that lack of correlation scares me because there doesn't appear to be any certainty that the perch contamination on lake beds are protected. And you look into the situation, you discover 7 different sources of future water releases that could conceivably disturb perch contamination on lake beds. And the first one is that 400 million gallons of water are pumped from the Columbia River to the 200 years every year. These are drinking water, septic systems, to run your sewage systems. The impact on the perch contamination of how this water is discharged is unknown. Millions of gallons are injected into the groundwater part of the pump and treat system. Impact on trapped contamination is unknown. Miles of drinking water in fire hydrant systems throughout 8 square miles is unknown, and that system was installed, some of it, well, 70 to 80 years ago. Some of it's been replaced, but from 2008 to 2018, there were 77 leaks in that major system with major impacts and major leaks when the impact of that water leaks are unknown. Flushing of one hydrant, and there's hundreds of hydrants, 30,000 gallons of water is released every time. Routine flushing of the drinking water system once a year. How many gallons there? A couple 100,000. Hydrant failure in one part of the project. The system broke when they were flushing it, and instead of 30,000, it was over 100 to 300,000 or more. Water is also used to control contaminated demolition dust resulting in large lakes. We'll see a picture of that in a minute. Flooding due to rapid snow melt over a frozen ground. In 1979, we had flooding at the tea farm, and I will show you a picture of that. Other areas were affected as well, but not documented. Okay, this is one of my favorite. Flooding due to heavy downpours during lightning and thunderstorms. And most people, the general public, do not understand the danger this has caused at Hanford. You get one of these intense cells during a thunderstorm, and it can drop 1 to 6 inches per hour over a small area in 15 to usually around 15 to 20, 30 minutes or less. I happen to be coming back at night, at 10 o'clock at night, and hit one of these cells. It rained so hard I had to pull off the highway close to FFTF. And I had to sit there for 20 minutes at night. I couldn't see out of my car. The rain was blasting on that. My wipers couldn't keep up with it. It rained so hard for 20 minutes. In that 20 minutes, the parking lot at FFTF is giant. It's a 5-acre parking lot. So there's this giant funnel, and took thousands of gallons of water into one of the FFT buildings. It destroyed over $10,000 worth of equipment. Also, it was that flood or an earlier one where DOE facilities in downtown Richland, one of our irrigation canals flooded the basement one and overflowed due to these and destroyed over tens of thousands of dollars worth of computers in the basement. So there's more water that can be delivered here than the average person thinks when you think about it in terms of the stuff. Flood damage over the last 80 years on the project itself is not, it occurred at times, but it wasn't documented. And lastly, examples of new caps are being put over tank farms to divert water to a side basin. Well, that means water is taken over a large area and put in a small area with lake beds there. The lake bed could take the water and push it back underneath the cap, or it would take it down into the water, but you'd have a more concentrated area there. Okay, so we got to get closer. I've got some photos in the movie at the end here. I just want to show you an example of corrosion. Look at the size of these pipes. This is part of our water system here. Look at, I mean, what do you think when you're looking at this thing? How many years of this life does this have left? It's past its design life, it looks like. We have water leaks, and when they have a water leak, a pipe's that big, it's huge. You put millions of gallons of water out, and nobody really knows where it flows and where it goes to, and whether it's going to disturb any of our perched water underneath the ground. We have demolition going on. Look at the spray they put on, but look at the lakes. And this happens to be in an area where there's lots of underground liquid discharge sites where the contamination is perched on these lake beds. And what's this water doing to that? And here again is pictures of lakes being around a demolition site. Another one, the pictures. This shows the picture of flood over the tea farm, and it just shows you water there flooding the thing. But here again, let's talk about this a minute, because DOE talks about using this as a site, as a future industrial site over the next several hundreds of years, thousands of years. And look at all the challenges you have if you have a lake bed sitting here with all the contamination perched on top of it. And this is one. Now, we've actually got hundreds of these and spread out. And again, DOE does not have a map that shows where these discharge sites are in relationship to where we know we're putting water. We know water is going to flow off the surface of industry, but most industry does have condensate and water discharge. And that's and you've got all these water line flushes, you've got water line breaks, You got water with all we talked about, demolition water. You also have climate change over the next several hundred years that may have some effect on groundwater, I'm not sure. And even back a few years ago, it was unbelievable. They were talking about putting a Black Rock Dam west of Hanford, which would have put a giant reservoir in there, would have raised the groundwater underneath our cribs and burial grounds. Okay, so the challenge here again is that you have a monitoring well here with all this water. Well, we're not going to get into that at this point. Just the point is that future water, we need a control water. If you're going to protect ancient lake beds and purge contamination, you have to be concerned about how water is going to be injected into the soil over the next 100 years. Okay, danger 5, and this will wrap this up. Here's the question, the concern about groundwater. You do a vertical flow, and let's just say that hypothetical that shows you the groundwater from Hanford will reach its peak in 1,000 years. And then if you do a modeling with a zigzag flow, which is the correct situation, the hypothetical would say 1,500 years. Well, okay, what does that mean? Well, if no contamination reaches the groundwater in 1,000 years, what happens? Well, everybody figures it's expensive to monitor groundwater. Maybe the contamination is frozen or trapped in the underneath 200 areas. And so when contamination reaches the groundwater in 1,500 years, what happens? There's no monitoring groundwater. It's not occurring. Results in elevated health risk for the public without public knowledge. Our expectations are, of course, that the conceptual models will be improved over the next several hundred years to ensure long-term safety. Well, I've gone over my time, but the conclusion is that part 2 helped you solve the mystery of how lake beds were formed. Part 3, you learned that even though we discovered lateral migration in 1947, it took almost 70 years before we used the word ancient lake beds and started getting involved. Part 4 showed you the mystery of how current activities are involved, particularly the extensive pump and treat system and the new technologies. Part 5 talked to you about the 5 potential dangers. You discovered in September 2021, the conclusions of Patel scientists or Pacific Northwest National Lab scientists, that there's insufficient knowledge of ancient lake beds to make intelligent decisions about cleanup. Now, that was made 9 months ago. Essentially the same conclusion as reported in the 1998 General Accounting Report 23 years earlier. Have we made progress, folks? You wonder how the Department of Energy can ensure public safety in the future without a greater knowledge of ancient lake beds. Maya, that's it. I'm going to put a slide up. These are my 4 suggested references, actually 2. And I really almost would like everybody to go, if you haven't visited this site, go and you can click on the Geology corner or the resource corner links. Will lead you to videos. You have to work hard to find them. The GAO report, the title says everything. You don't need to even open up to read 50 pages that say the same thing. Understanding of waste migration is inadequate for key decisions. The one I want you to see, though, is, and don't let the 780 pages for the groundwater report for 2020. That is written for the general public and give you all this amazing, it's like an encyclopedia. You don't have to read all 70. What you do is you go to the specific site, the 200 West or East area, and they give you this detail and very full knowledge of that. So that's the one I only want to recommend. And this, the last one here I've used, I basically pulled out from this document that Patel issued 9 months ago, the key points to that. So, but I'd recommend going to just go to your search engine here, go to enter Hanford groundwater monitoring report. And at that, I'm going to bail out of this.